So I would like to continue the previous class. So next one we can calculating the direct shear stress to act on the particular key. So shear stress is equal to 2T divided by D into W into L. So 2 into T 0.53, that is called as torque. So this is called as diameter. This is called as width of the key. So width of the key will be a 0.4 and the length of the key will be a 0.3. So we calculating those values, we are getting the final value of 0.75 Newton per mm square. So this is called as direct shear stress act on the key dimension part. So finally we can check with the crushing stress value. So that can be a sigma k is equal to 4T divided by D into L into H. So T is torque, D is nothing but a diameter, this is called as length of the key, this is called as height of the key. So 4 into as well as the torque value 0.53 divided by 1.6 into length will be a 2.3 and the height will be a 0.3. So calculating the upper values and lower values, finally we are getting the value like 2.3 Newton per mm square. So this is the called as crushing stress value of the key. So next one would like to check with the dimension of hub. So in the previous part the shaft can be coupled with the key is mounted with the hub. So now we can design the now we can calculate the diameter as well as the key dimensions. Now we go with the hub dimensions. So that is called as step number 3. So in the dimension of hub we have 3 points, three major points to be calculated. So first one, length of the hub. So it can be a 1.5 into D. So 1.5 into, so diameter value is like 1.6. So we can multiply with the both values, we are getting the 2.3 mm. So this is called as a length of the hub. So second one, outside of the diameter. So capital D is equal to 2 into small d. So 2 into 1.6 is equal to 3.2 mm. So this is called as a outer dia of the hub. So this is, or example is, this is called as shaft dia. So small d. So this is key dimension. After the key dimension, we go with the hub. So comparatively, the normal diameter is greater than the hub diameter, outer diameter. That is called as 3.2. So you can be checking 1.6 is greater than by 3.2. So this is called as a hub diameter. So step number 3, stresses in hub. So it is denoted by tau h is equal to 16T divided by pi d cube into 1 minus K4. So this K parameter, how do we can calculate? K is equal to small d divided by capital D. So it can be a 1.6 divided by 3.2, it means that 0.5. So this is the value we are getting. So apply with this above formula, how much stress can be act on the particular hub, we can be easily evaluated. So I am just putting the value of the above formula, 16 into torque value and pi into D value is unknown. So D value is 3.2 power cube into 1 minus 0.53 power 4. So summarizing all the values, so stress act in the particular hub is equal to 0.095, so Newton per mm square. Let me check it. It can be a lesser of 1 Newton per mm square. That's our design of hub will be a safer side. So it can be a go with the above or more than the 1 Newton per mm square or more than the 1. So that can be we want to summarize the previous things, because more than 1 means the design will be a not safer one. So less than 1 will be a safer one. Please make a note of it. So now finally we can come to the end of the problem. So the last step it would be a dimension of flange. So step number 4 is equal to dimension of flange. in the particular dimension of flange, we can calculating the thickness of the flange as well as the stress including the flange. So thickness of the flange is nothing but how much thickness that can be inbuilt with the bushed pin type. So that can be calculated with the help of one single formula. So TF, thickness of the flange is equal to 0.5 diameter. So 0.5 into 1.6, we are getting the 0.8 mm. So this is called as thickness of the flange. If you have any queries that we ask or otherwise, we can see on the next videos.